Jai Hind everyone. My name is Gunjan Saxena, Assistant Professor, Ajay Kumar Garg Engineering College. So I am back in the series of DA lectures, and today's topic is spanning tree. This topic is very important for the purpose of university exam or your university exam, anything else. So what are the spanning tree, or in this particular lecture we are just going to discuss about the introduction of this spanning tree and the approaches which are used to find a spanning tree from any graphs. So let's start. These are the outlines for today's lecture. In today's lecture I am just covering the introduction about the spanning tree. After that, how we make a spanning tree, and after that what is the minimum cost spanning tree, then properties of this, different type of approaches like Kruskal and Prims, and solving the example for these particular approaches. So what are these spanning tree? Basically in the graph there are approaches to communicate or use the different edges and the vertices for finding the spanning tree of the graph. So the definition of this particular spanning tree is like a spanning tree can be defined as a subgraph of an undirected connected graph. It includes all the vertices along the least possible number of edges. If any vertex is missed, it is not a spanning tree. A spanning tree is a subset of the graph that does not have a cycle, and it also can't be disconnected. That means if we have a graph and we are just traversing all the vertices, what are the rules? We need to traverse all the vertices, not every edges, because in the spanning tree there is not a closed loop, or we can say there is not a cycle formed by the traversing rule. So in short, what is spanning tree? Spanning tree is just a traversal part, or we can say the traversing of all the vertices without making a cycle. So in any connected graph, or we can say in any directed graph or undirected graph, we can have a n to the power n minus 2 number of spanning tree, where the n are number of vertices, or we can say are nodes. Suppose we have n equals to 5, that means we have number of vertices which is 5. So according to this formula, which is n to the power n minus 2, we have 5 to the power 5 minus 2, that is 125. That means we have 125 possible spanning tree. But in case of minimum cost spanning tree, as we know, in each and every graph, suppose we are assuming this graph. Suppose this is the graph. So what we are saying, we have 4 vertices, that means 4 to the power 4 minus 2, that is 4 to the power 2, which is 16. That means we have possibly 16 spanning tree. But in terms of cost, we know in every graph there are some edges. That means we have a path from N to A from V, or we can say D to B or B to D. We have some cost. This cost is maybe 10, 5, 2 and 3. So what is the minimum cost spanning tree? We are considering the spanning tree from the 16 possible spanning tree which is having a minimum cost. So in the next slide, I am giving the example, or we can say I am showing all the possible spanning tree of this particular graph, which is having n to the n, the value of n, which is 4. So according to the formula, n to the power n minus 2, which is 4 minus 2, equals to n square. That means 16. We have 16 possible spanning tree for this particular graph, but in case of minimum cost spanning tree, we are having a minimum cost which is connected in the form of connected, or we can say from these spanning tree we are choosing this particular which is having a minimum cost. So we are seeing this is having 7, this is having 8, 9, 6, 9, 12, 11, 10, 9, 10, 10, which is 13, and 12, 15, 14, and this is 11, again 13. So as we are watching this particular graph having a minimum cost which is 6. So these are 16. These 16 are the spanning tree, and this one which is having a minimum cost which is called as minimum cost spanning tree. So there are some properties. This is the property number 1, number of spanning tree in a complete graph. Firstly, these properties are for complete graph, the K graph. Maybe this is the K3, which is the complete graph, or in a planar, which graph is having 3 node or 3 edges to complete this graph, which is known as K3, or we can say K4. In any complete graph, the number of spanning tree is always n to the power n minus 2, which is already covered in previous slide. So the property number 2, one edge addition made the cyclic form in the tree. In any spanning tree, suppose we are making a spanning tree from a graph. If we are adding any vertices, any edges in the spanning tree which make the spanning tree in a cyclic form. So if this is a spanning tree and I am just adding one node which will create a cycle over here. So this is the property number 2. Next one is property number 3, which is number of edge removal from graph for spanning tree, which is E minus V minus 1. That means for any graph, as I am taking a K3, K4, you can take K5 also. What the property 3 said, which is said E minus V plus 1, where the number of edges which is 3 minus 3 plus 1. That means from this particular graph, if we remove edge number 1, that means one edge from this particular graph, which will create a spanning tree from this particular graph. So as I already covered, already discussed about the spanning tree and what is the minimum cost spanning tree, and after that these are 2 approaches to find the minimum cost spanning tree. Number 1 is Kruskal and second one is Prim. So in this particular method, or we can say this particular approach, the Kruskal is used to find the minimum spanning tree for the connected weighted graph. The main target of this particular algorithm is to find the subset of edges by using which we can traverse every vertices of the graph. It follows the greedy approach to find the optimal solution at the every stage. So what is the quick algorithm about this approach? First, we have to sort all the edges in the form of weight in the ascending order. Now it can take the edge from the lowest weight and add to the spanning tree. If the edge to be added create a cycle, then ignore this particular edge. Continue to add the edges until we reach all the vertices and a minimum spanning tree is created. One thing remember, in this particular approach, we follow the concept of forest. Okay. Now, so what we are doing, firstly we draw the given question, and as the step number 1, just write down all the edges. I'm just write down the all the edges from the with the weight in this particular table. Now what is the step number 1? Just sort these edges by the weights in the increasing order. Okay, and then take the edge from one by one and reject the edge if it will create a circuit. So what we are doing, so basically first we are taking edge number 1, which is AB. AB is selected. Number 2, which is DE. So this is the DE. As I already talked about the concept of forest, just see this particular way. Here 2 edges are there, which is B and this is A. This is weight as 1 and this is D and E. So in this particular situation, there is 2 individual disconnection tree, or we can say graphs are there. That's why I am telling about this Kruskal is follow the rule of forest. In this particular situation, this is a forest situation. Okay. Now, in particular, in the next, we are having BC. We are added because no circle is there. After that, CD. So CD is also taken. If we taking AE, it will create a circle. If we take AC, it will also create a circle. If we take AD, it also create a circle. So, as a theoretical manner is said, we are arranging the edges in increasing order, and one by one we are picking all the edges until we cover all the vertices. If any edges arises and which will create a circuit or we can say cycle, just ignore them. So this is the concept of Kruskal. These are the steps, or we can say standard steps for the Kruskal algorithm. What they said, create a forest F in such a way that every vertex of a graph is a separate tree. Create a set E that contain all the edges. After then repeat step 4 and 5 until, or we can say while E is not empty and F is not a spanning tree. Remove an edge from E with the minimum weight. Step number 5, if the edge obtained in step number 4, connect 2 different trees, then add it to the forest F, else discard the edges. So these are the standard steps for Kruskal algorithm. Now, the next is Prim's algorithm. It is a greedy algorithm that is used to find the minimum spanning tree from a graph. Prim algorithm find the subset of edges that include every vertex of the graph such that the sum of weight of the edge is minimized. What is the basic difference between Kruskal and Prim? In Kruskal algorithm, as we seen, we are taking, or we can say we are connecting with the edges only, or we can say we are taking as a priority of edge concept. But in the Prim's method, we are taking as a priority the vertices. We are just choosing any arbitrary vertex and go to the next descendant vertices. Okay, so in Prim's method, first we have to initialize a minimum spanning tree with a randomly chosen vertex, or we can say any arbitrary node. But in your university exam, you are just taking the symmetry. If the vertex is in the form of ABC, just take a node as a arbitrary node, or if the vertices are 1, 2, 3, just take a node number 1 as an arbitrary node. But this is not a rule. This is the just way to start. In the algorithm, we can take any node. Now, we have to find all the edges that connect the tree in the above step with the new vertices from the edge found. Select the minimum edge and add it to the tree. Repeat step number 2 until the minimum spanning tree is formed. So, this is the algorithm. Select the starting vertex, repeat the step number 3 and step number 4 until there are freeing the vertices. Select an edge E, or we can say the arbitrary node E connecting the tree vertex, and freeze the vertex that has a minimum weight. Add the selected edge and the vertices to the minimum spanning tree and end of the loop. So how this particular prim is work, as this is the question given, we are just, what we are doing, we are initially taking any node. I am just taking a node A as an arbitrary node. So now we have to check, we have to consider the adjacent vertex of A. There is only adjacent vertex which is C. That means we have to go A to C. As we have no option, if we have some another edge, suppose we have A to E and having the cost 1, or we can say cost 2, then the cost, according to the cost, we go to A to E rather than A to C. So there is only vertex, or we can say there is only adjacent which is C. Now we go to A to C. So the cost is 3. Now, in our criteria, or we can say in our stack, we have also a vertex C, and we consider, or we can check all the adjacent of this C vertices, which are B is the adjacent for C, D is the adjacent of C, E is the adjacent of C. So we have 3 areas, or we can say we have 3 options. We can move, we can go C to B, we can go C to D, we can go C to E. But what the algorithm said, which is having minimum weight, we are taking these edges only. So in this particular way, or we can say in this particular traversing, we have C to D, which is the minimum cost, rather than C to B and C to E. We are just taking this particular way. Sorry, this is 2. We are taking C to D. Now, when D is arises, we have E, we have B. So we can go through C to E also, we can go D to E also, but what we are taking, what we are considering the minimum cost. Suppose if I want to discover this particular E by using C, then the cost is 6. And if we are discover this particular E by using D, the cost is 1. So we can't take the path from C to E because the cost is 6. So we are taking D to E as the cost is 1. Okay. So D to E is already done. Now, discovery of E to C, which make the cycle. If we are taking, now what is the next vertex is to be discovered, which is B. So, for the B node, we can go to C to B and we can go to D to B. So, if we are taking D to B, we are having the cost of 4, and if we are taking C to B, as we are seeing now, the adjacent of B in the final graph, we are having only 2 adjacent, which is D and C. If we are taking B to C vertices, the cost added, which is 10. And if we are taking B to D, the cost added, which is 4. So obviously we can take this cost. So for this given question, what is the final cost? The cost is 4 plus 2 plus 3 plus 1, which is 8, 9, 10, 11, 12, which is 12. So this is the minimum cost of this particular spanning tree. As I have already discussed, any graph having more than a spanning tree, but every graph have only one spanning tree which is having a minimum cost. So the prim and Kruskal both are using to finding the minimum cost, but Both the process, both the approaches are different. In Kruskal algorithm, we are just considering the spanning tree, by considering the ages, and in the term or in the form of prim, or we can say in prim algorithm, we are just taking as a vertices wise, or we can say the node wise. So, in just a sum up of this particular lecture, in today's lecture, we are just discussing about the spanning tree. So, in short, the spanning tree is the approach and the way to just span all the vertices of any given graph with some limitation, or we can say with some rules. We need to discover all the vertices, no necessary to find all the edges, as the phenomena is just covering all the vertices, but the make sure no circle form in this particular scenario. So, what is the minimum cost spanning tree? As I already discussed, graph having more than one spanning tree, but what is minimum cost spanning tree? If we are considering the weight under the two vertices, we are just considering a minimum total cost of these particular span tour. Okay. There are two approaches for doing so. There are Kruskal algorithm and the prim algorithm. In Kruskal algorithm, when we are going to travel, or we can say we are going to span the all vertices, we are just considering the edges in the ascending order, and after then we are picking up one by one edges. If the circle is formed, we just reject the edge. This process is looping and lopping until all the vertices have to be covered. In the prim algorithm, rather than we are taking edges, we are just considering the vertices only. We are just taking any arbitrary vertex, just seeing the adjacent vertex of this particular vertex, which is having minimum cost, or we can say minimum edge area. We are just selecting this particular vertex. So, thank you very much. Now, ending of this lecture. We will again meet in continuing series. Okay, bye.